Okay, so we just finished up looking at stress, and stress was a measure of how much force was moving through a area on an object. Whenever we put an object under stress, so we put a force on that object, it's very likely that we're going to create some amount of stretching. Okay, so when we talk about stretching in terms of engineering, what we use is the term strain. And strain is a measure of how much the material has stretched when it is under stress. So if we put some object under tension, it will have a couple things. It'll have its original length, so when we don't have any stress on the material. And then if we do stress it, so either under tension or compression, it will have a small change. And the measure of this change, the change of length divided by the original length, is what we quantify as strain. Okay, so what is strain? Well, strain, as we said, is a change of length, or a way we measure a change of length in a material, and it's caused by a stress. So a stress causes a stretching, and we quantify that as strain. And strain uses the symbol epsilon, so it's this sort of scripted E, and it's our change of length compared to the original length. And sometimes the change of length, we use kind of a scripted L instead of the standard uppercase L, just to quantify the difference between the two. So this guy is really my change of length divided by my original length. And if we look at the units, we have a length divided by a length. So usually what happens is this is unitless. So if we had like millimeters and millimeters, yeah, those guys would likely cancel each other out and leave nothing. However, sometimes we use, or we'll leave that unit in strain. So we may say the strain was 0.004 millimeters per millimeter. Or else what we might use sometimes is different units. So sometimes you may have, it's going to be a amount of strain which is going to be like millimeters per meter or something. So maybe that it becomes a larger value for something that is changing very little. So we have a larger value. But typically you're just going to have E as a unitless number if both of those units cancel out. Okay, so let's do an example here. Steel beam is 2 meters long when unloaded. It is compressed using a force of 20 kilonewtons, and then the compressed length is 1.988 meters. What was the strain in this beam? Okay, so we need to know a few things. So we need to know L, which is our original length. It's going to be 2 meters. Okay, we're going to need to know a change in length. So if we are measuring a change in length, it's going to be what do we have now compared to what did we have previously. Okay, so what we have now is 1.988 meters minus what we had previously, 0.00 meters. And if we check that, 1.988 minus 2.000, we're going to get negative 0.012 meters. Negative, so it did compress, so we have a negative change in length. The length got smaller. Okay, so that's okay. When we calculate strain, in this case, the strain would be my change of length compared to my length. So negative 0.012 compared to 2.000, both of those guys in meters. And what I would get is negative 6 times 10 to the negative 3. And that would be meters per meter, or else, because those cancel out, just no units. Okay. The negative strain makes me think that it was compressed. Okay. But often what we really care about is just the value. So what was the magnitude of the strain? And that's going to be important for us in calculations. Just going to step aside from materials for a second, and we're going to look at some specific examples involving a solid material known as a spring. As part of your third class content, you do have some questions that could be asked relating to springs. However, you don't have really any content within your third class textbooks on springs. So we're going to talk a little bit about springs, and we're going to relate that to some of the strength of material content that we've been covering. Okay, so first of all, what we need to know is how does a spring react when it's under load. So if I was to take a look at my spring and I was to stretch it, as I increase the force, it seems that my spring stretches more and more and more. Also, the further that I stretch it, the more essentially energy it has inside of that spring. And we're going to try and make sense of some of the equations around that and how we go about looking at spring calculations. Okay, so first of all, if I was to graph what happened inside of my spring. Okay, so if I was to draw a little graph here, and I was to graph, let's say, the force that I was pulling down with on the spring, and maybe I could use down here for the change in length. So if I was to quantify how much was changing with my spring as it stretched, what I would see is that at 0, 0, I would have no stretch and no force. As I added force, my spring would start to stretch, and I have a linear relationship for most springs. Okay, linear meaning that that is a straight line. So for instance, if I was to add, I don't know, 100 newtons of force, and maybe that meant that it stretched, I don't know, let's say 1 centimeter. If I added 200 newtons of force, the linear relationship means that now this guy has stretched 2 centimeters, and so on and so on. So it's very predictable how much stretch I'm going to have based on given force that's added. Okay. Now, that was for one spring. However, all springs are going to have different characteristics. So for instance, I might have a spring that is stronger. Okay, so a stronger spring would require more force to stretch a shorter distance. And what that means is that a stronger spring would be still a straight line, but it would be a steeper line. So that's a stronger spring. And if we had a weaker spring, it would stretch a larger distance with less force being added. So this is my weaker spring. So what it tells me is that something to do with that angle of that line is going to indicate for me what is the strength, or how stiff is that spring. Okay, and so we have a case where when we look at the spring, the slope of this line, or the steepness of that line, is going to be equal to what's known as my spring constant. Okay, and that we give the the value or variable k. Okay. So the slope is a rise over run. Which means that k is going to be equal to the rise, which is a measure of the force, compared to the run, which would be the change in length. And if I rearrange that, I get an equation: force is equal to k times the change in length. And that's a pretty universal equation for a spring, and it's what's known as Hooke's law. So we have a way to measure how a spring performs, and we have Hooke's law to demonstrate that for us. One of the other components that you need to be able to do at your third class level is calculate the energy in a spring. So let's do a little bit of backtracking here, and what we're going to do is look at some mechanics. In mechanics, if I look at work, which is really my sort of first bit of energy that I look at, work, sometimes we say, is a force applied over a distance. Okay. And I'm going to draw a little graph for that. So if I had a force and I had my distance, and maybe I applied, I don't know, 100 newtons of force, and that was applied over a distance of 1 meter. Well, in this case, my work is equal to the force times the distance. So 100 newtons consistently applied over the span of a meter gives me 100 Newton meters, and that is also known as a joule of energy. Okay, so we could calculate work. One thing that's kind of interesting about this, where I graphed it, is that if I look at this equation, so work is equal to 100 newtons times 1 meter, really what I'm doing is I'm multiplying my 100 newtons by 1 meter. And the result of that is that I've created a rectangle. And that rectangle shows up on the graph. And the importance of that rectangle is that my area is equal to work. So the area of a graph, force and distance, is going to relate to work. Okay, so let's see if we can figure out, with a spring that looks just a little bit different, how we would quantify work. So my spring does not have a horizontal line, so the force does not stay constant throughout the entire stretch of that spring. My force increases. So if I'm to figure out my work, or the energy inside of that spring, what I'd like to do is, for some given stretch, be able to find the area. And the area, in this case, is no longer a rectangle, but is a triangle. And it's going to be 1/2 base times the height for a triangle. Well, in my spring, I had force and I had change of x. So my area is going to be equal to 1/2 times the force times the change in length. And this would be a measure of the energy inside of a spring. And I can go one step further with this equation, which is to bring in what I know from Hooke's law and substitute that for my force. So my force term here will get replaced with K times the change of length. And what I have is my final equation, which is going to say that the energy in a spring E in a spring is going to be equal to 1/2 times Kx, or change of x, times my change of x, or my energy of my spring is equal to 1/2 K times the change of length squared. You got one problem. You have to be able to do this. However, give you the caution, not in the supplement. So you're going to have to be able to remember this in case you have a question about springs. So there isn't any information on springs in the academic supplement. You're going to have to be able to find it. Okay, let's do a practice question on springs. So a spring, sure, I got a little spring here, and when it's unloaded, so 14 centimeters, and I add some mass to it, and it stretches, and I guess that was 1.2 kilos, and that then stretched it to 23 centimeters. Okay. I want to know a few things. What is the spring constant? How much energy is stored in it? And what mass would need to be added in order to stretch the spring to 30 centimeters? Okay, so first thing that we have to do is let's talk about K. K is equal to the spring constant, which is a measure of the force compared to the change in length. Okay, so the force that I have, 1.2 kilograms. When we talk about a mass hanging down, that's not a force, it's a mass. So my force is going to be equal to 1.2 kilograms times gravity, 9.81 meters per second squared. And I'm going to have a force of 11.772 newtons. Okay. My change in length is going to be the difference between what I am compared to what I started. So 23 centimeters minus 14 centimeters, and that's going to be 9 centimeters. Or if I convert that maybe to meters, 0.09 meters. Okay. It's important to get my units into the right values. So you see I've got newtons and I've got meters, because when I use that equation, work is equal to force times distance, don't forget that my force was a newton and my distance was a meter, and that ended up giving me a work in Newton meters or joules. Okay, so important that we get everything into newtons and meters in these questions. It's going to be helpful to make sure we've got the right answers at the end. Okay, so K is equal to my force divided by the change of length, so is going to be equal to 11.772 newtons compared to 0.09 meters. 130.8, and that would be newtons per meter would be my units for K. Okay, so that's number one. Number two, energy is going to be equal to 1/2 K times my change of length squared. So 1/2 times 130.8 newtons per meter times 0.09 meters squared. And what I get is 1.05948. And if I look at the units, I have a newton. My meter on the bottom cancels out with one of my meters on the top, which means I have a meter on top, and that ends up being 1.06. Let's say Newton meters is equivalent to a joule. Okay, question number 3. So we have a couple of approaches we can take. One is we can realize that there's a linear relationship. So really just becomes a ratio question. So 1.2 kilograms caused a stretch of 0.09 meters. What would cause a stretch of, well, let's see, 30 minus 14, so 16 centimeters of total change of length if it's 30 centimeters long. And we could just use it as a ratio, and so then from there we cross multiply and figure out for our x. So 1.2 times 0.16 divided by 0.09. 1.2 times 0.16 divided by 0.09 gives me an answer equal to 2.13, and that would be units of kilograms. Okay, so that's one approach that you could take. And your other approach that you could take would be, again, to figure out using K. So K is equal to force divided by the change in length. So force is equal to K times the change in length. (130.8 newtons per meter times 0.16 meters. Gives you a force of 20.928 newtons. But of course we have to be careful that we have gravity, so my mass is going to be equal to the force divided by gravity, 20.928 newtons divided by 9.81, 2.13 kilograms would be my answer. Okay, so a couple of approaches there if you have a question like that. Okay, so that's it for strain and springs. In the next section, we're going to look at, instead of springs, what if we just stretch a general material, and what are some terms that we might use, and how can we calculate changes of length and other components with a solid material.